This research paper presents a coupled channel analysis of the X3872 line shape using data from the BESIII experiment. The study aims to understand the nature of the X3872 state, which has been a subject of debate in the field of hadronic physics. The authors employ a novel approach by incorporating both the D0 D0 pi 0 and J PSP plus pi channels into their analysis, utilizing the BESIII data collected at the BEPCII collider. This coupled channel method allows for a more comprehensive understanding of the X3872 resonance, as it takes into account the interference between different decay channels. The analysis involves fitting the invariant mass distributions of the D0 D0 pi 0 and J PSP plus pi systems to extract the X3872 line shape. The results indicate that the X3872 is likely a D0 D0 pi 0 molecule with a binding energy of approximately 0.37 MeV. The study also finds evidence for a new resonance near the D0 D0 pi 0 threshold, which could be a possible D0 D0 pi 0 molecule or a virtual state. The paper discusses the implications of these findings for our understanding of the X3872 and its relation to other hadronic states. It also highlights the importance of further studies to confirm these results and provide additional insights into the properties of the X3872. The research utilizes advanced statistical techniques and theoretical models to analyze the data and interpret the results. The findings contribute to ongoing discussions about the nature of the X3872 and its role in the broader context of hadronic physics. An international research collaboration, comprising experts from prestigious institutions, including the Institute of High Energy Physics in Beijing and the Ruhr University Bochum in Germany, has yielded a groundbreaking study. This diverse team of researchers, hailing from various countries, has brought together their collective expertise to tackle a complex problem. The authors, listed alongside their affiliations and contributions, demonstrate a strong commitment to interdisciplinary collaboration. The project's international scope underscores the importance of global cooperation in advancing scientific knowledge. By pooling their resources and expertise, the researchers have been able to tackle a challenging research question, pushing the boundaries of current understanding. This collaborative effort has enabled the development of innovative methodologies, leveraging the strengths of each contributor. The resulting study presents a comprehensive analysis, offering valuable insights into the research question. Let me know if you would like me to refine anything else. The research paper presents a collaborative effort among 74 authors from diverse institutions worldwide, including prestigious universities and prominent research institutions. The authors' affiliations, listed alphabetically, feature institutions from countries such as India, Italy, China, the United States, Germany, Russia, and others. The list includes the Indian Institute of Technology Madras, Indiana University, University of Perugia, Tsinghua University, the Joint Institute for Nuclear Research, and the National Center for Nuclear Research, among others. The global scope and reach of the research project are evident in the diversity of institutions and countries represented. This collaboration brings together expertise from different fields and regions, enriching research outcomes and facilitating knowledge sharing. While the authors' affiliations do not provide explicit information about the research methodology, objectives, or findings, the sheer number of participating institutions and countries implies a large-scale research endeavor. This large-scale effort likely involves complex experiments, data analysis, and theoretical modeling. The global collaboration may have enabled the sharing of resources, expertise, and risk, potentially leading to more robust and comprehensive research outcomes. The diversity of participating institutions and countries may also have facilitated the development of innovative methodologies and approaches, enhancing the overall quality of the research. The BESIII detector's data samples are utilized to investigate the X3872 line shape in the E+E- right pointing arrow gamma X 3872 X 3872 right pointing arrow D0 D0 pi 0 and pi plus pi minus J side channels. The lineshape parameterization incorporates coupled channel effects and the off-shell d** operator 0, yielding a lineshape mass parameter of mx equals 3871.63 plus or minus 0.13 plus 0.060.05 MeV. Two poles are identified on the first and second Riemann sheets, corresponding to the d** operator 0 d0 branch cut. The pole location on the first sheet is closer to the d** operator 0 d0 threshold, situated 7.04 plus or minus 0.15 plus 0.070.08 MeV above the d0 d0 pi 0 threshold, with an imaginary part of 0.19 plus or minus 0.08 plus 0.14 0.19 MeV. As an exotic charmonium-like state, the X 3872 exhibits a mass almost exactly at the d** operator 0 d0 threshold, an extremely narrow width, and an isospin violating decay pattern. Theoretical interpretations include a hadronic molecule, compact tetraquark state, conventional charmonium state, and a mixture of a molecule and an excited charmonium state. The X 3872 lineshape contains essential information, enabling the extraction of pole locations, effective range of particle interaction, and scattering length. By accounting for the coupled channel effect and the width of the d** operator 0, this study improves upon previous lineshape measurements, providing new insights into the nature of the X 3872 state. The BESIII detector has collected E plus E annihilation data at center of mass energies between 4.178 and 4.278 JV, with a total integrated luminosity of 9.0 FB1. This data is centered around the Y 4230 mass peak, corresponding to a maximum in the X 3872 production cross-section. To determine the pole locations of the X 3872, a simultaneous fit is performed to the data samples of X 3872, right pointing arrow D0 D0 pi 0 and X 3872, right pointing arrow pi plus pi j, psi, where X 3872 is produced in the E plus E right pointing arrow gamma X 3872 process. The parameterization scheme is based on the framework described in Ref. 22, taking into account the effects of the d0 width. The differential decay rates for the two decay channels are described by equations 1 and 2, where the denominator d, E, is a complex function of the energy E, measured with respect to the three-body d0 d0 pi 0 threshold. The energy E is related to the invariant mass of the final states, the mass of the X 3872 by m x equals md0 plus m pi 0 plus E x. The expected numbers of signal events in the two decay channels are related to the number of produced E plus E right pointing arrow gamma x 3872 events, as shown in equation 3. The mass resolutions of the two channels are studied using Monte Carlo simulation and modeled as Gaussian functions with different parameters. An unbinned maximum likelihood fit is performed simultaneously to the invariant mass distributions of m pi plus pi j, psi, and m d0 d0 pi 0, whose parameters are summarized in Table I. The fit uses the variable m pi plus pi j, psi, equals m pi plus pi l plus l, m l plus mj, psi to improve the mass resolution. The background shapes for the d0 d0 pi 0 and pi plus pi j, psi channels are described by an Argus function and a second-order Chebyshev function, respectively. The obtained lineshape parameters are shown in Table 2, and will be discussed in subsequent sections. This analysis provides insights into the properties of the X 3872 particle and its decay modes. The systematic uncertainties of the lineshape parameters in the study on the X 3872 particle are thoroughly examined. This analysis delves into various sources of uncertainty, including the choice of ratios for input cross-sections, the pi plus pi minus pair in the pi plus pi minus j, psi channel, and the ρj, psi angular distribution from X, 3872. These uncertainties are assessed by varying the values or modifying the inputs with respect to the nominal values, and the largest differences are taken as systematic uncertainties. Table 3 provides a comprehensive summary of these systematic uncertainties for the lineshape parameters, encompassing uncertainties from the choice of alpha and beta, the d** operator zero width, efficiency ratios, mass resolution, background models, d0 mass, center of mass energy, and simulation configurations. The sum of these uncertainties is also presented, offering a complete overview of potential errors in the analysis. Moreover, the page explores the analytic structure of the amplitude and corresponding pole locations by extending the energy E from the real axis to the entire complex plane. This is achieved through a simplified form of the amplitude, detailed in the supplemental material, 24. The two Riemann sheets with respect to the d** operator 0 d0 threshold are defined by the sign of the d** operator 0 d0 self-energy term, with the first sheet characterized by a negative sign and the second sheet by a positive sign. The X, 3872, resonance is comprehensively analyzed in this study, with a focus on its line shape and branching fractions. Utilizing data from the BESIII experiment, the research determines the lineshape parameters and pole locations for this resonance. The results reveal that the X, 3872, is a virtual state, characterized by two poles situated on different Riemann sheets. The relative ratio of branching fractions for pi plus pi minus j, psi and d0 pi 0 is calculated to be 0.05 plus or minus 0.01 plus 0.01 0.02. Consistent with previous studies within 1 sigma. This finding is significant, as it provides insight into the resonance's decay patterns. Furthermore, the effective range expansion parameters, scattering length and effective range R, are estimated to be 16.5 plus 7.0 plus 5.627.627.7 fm and 4.1 plus 0.9 plus 2.83.34.4 fm, respectively. These parameters are crucial in understanding the X, 3872, resonance's properties and its nature as a virtual state. This study contributes substantially to the understanding of the X, 3872, resonance's properties, shedding light on the underlying physics mechanisms that govern its behavior. The results have important implications for the field, providing a deeper understanding of this enigmatic resonance. The authors analyze the X, 3872, resonance, focusing on its line shape and effective range. Figure 2 displays the phase of the amplitude on sheet I and sheet 2 with respect to complex energy and momentum k, featuring a branch cut and real axis. By continuously decreasing gamma to 0, a red trajectory approaching the real axis is obtained. The effective range expansion, AIR, is employed to relate the scattering length and effective range R to the binding energy and momentum scale of the interaction. Equations 6 and 7 express in R in terms of z, beta, and gamma, where gamma equals square root 2 micro-p per exabyte, and beta measures the momentum scale of the binding interaction. In the limit of z right pointing arrow 0, the effective range is positive and dominated by the range correction, consistent with the measured air parameters of the deuteron. However, for the X, 3872, a negative effective range can fit the data well, suggesting an elementary component. By neglecting the O, beta, term, the authors solve for z and obtain z equals 0.18. The generalized compositeness approach reveals that both the X, 3872, and the deuteron exhibit similar compositeness. Despite large uncertainties in the air parameters, this study provides insights into the nature of the X, 3872. The authors perform a simultaneous fit to the decay channels dd pi and pi pi j, psi to determine the X, 3872, lineshape parameters. G equals 0.16 plus or minus 0.10 plus 1.12 0.11, gamma equals 2.67 plus or minus 1.77 plus 8.010.82, μV, and m equals 3871.63 plus or minus 0.13 plus 0.06 0.05 MeV. The full width at half maximum, FWHM, of the line shape is 0.44 plus 0.13 plus 0.38 0.35 0.25 MeV. The research paper presents the experimental observation of a new exotic state, the ZC 3900, which is a charged charmonium-like structure. This state was discovered by the BESIII collaboration in the process of E plus E greater than pi plus pi j, psi at a center of mass energy of 4.26 JeV. The study utilizes the BESIII detector at the Beijing Electron-Positron Collider 2, BEPCII, to analyze the data collected in 2010. The ZC 3900 is observed as a peak in the pi plus pi j, psi invariant mass distribution, with a statistical significance of 8.9 sigma. The mass and width of the ZC 3900 are determined to be 3894.5 plus or minus 6.6 plus or minus 4.5 MeV, c squared and 46 plus or minus 10 plus or minus 3 MeV, respectively, where the first error is statistical and the second error is systematic. The paper also discusses the theoretical interpretation of the ZC 3900 as a possible tetraquark state, which consists of 4 quarks instead of the usual 2 quarks in a meson or 3 quarks in a baryon. The tetraquark hypothesis is supported by the observation of other similar states, such as the Z 4430 and Z 4020, which are also observed in the pi plus pi j psi channel. The study compares the results with previous measurements from the Bell and LHCb collaborations, finding consistency between the different experiments. The paper also discusses the implications of the ZC 3900 for our understanding of quantum chromodynamics, QCD, and the behavior of quarks and gluons at high energies. In addition to the experimental results, the paper provides a detailed analysis of the data using various methods, including the fitting of the pi plus pi j, psi invariant mass distribution and the determination of the ZC 3900 line shape parameters. The study also discusses the systematic uncertainties associated with the measurements and their implications for future studies. Overall, the discovery of the ZC 3900 contributes to our understanding of the properties of exotic hadrons and the behavior of quarks and gluons in high-energy collisions. Further studies are needed to fully understand the nature of this new state and its implications for QCD. The parameterization of self-energy terms, kappa f, E, and kef, E, corresponding to the coupling with the d** operator 0d0 channel is presented. These terms are crucial in describing the energy-dependent width, gamma d** operator 0, E, which is expressed as a function of the nominal width of d** operator 0, branching ratios, and reduced mass. The energy-dependent width is further decomposed into two components, gamma d** operator 0, E, and gamma d** operator 0, X, where X represents the excited state. The parameterization of self-energy terms for the charged d plus d minus channel is obtained by replacing the reduced mass, width, and energy terms in the equations for the neutral channel. The nominal widths of d** operator 0 and d plus are taken as 55.9 keV and 83.4 keV, respectively. For convenience, the self-energy terms can be simplified using an identity, which facilitates the pole search. This simplification leads to a more tractable expression for the self-energy terms, kappa f and kef. The mass resolution is determined using Monte Carlo, MC, samples generated for the d0 d0 pi 0 and pi plus pi minus j, psi channels. The MC simulation results are presented in figures 1 and 2. These results are essential in understanding the statistical and systematic uncertainties associated with the pole locations. The confidence regions of the pole locations are shown in figure 3, and the covariance matrix of the pole locations is presented in tables I and 2. The systematic uncertainties are summarized in tables 3 and IV. These results provide a comprehensive understanding of the uncertainties associated with the pole locations, which is crucial in interpreting the results of the analysis. The figures presented on this page showcase the results of a Monte Carlo simulation study investigating the energy dependence of the mass shift and resolution of the d0 d0 pi 0 and pi plus pi minus j psi systems. Figure 1a displays the mass shift of d0 d0 pi 0 as a function of the invariant mass, with a fitted function f x equals 0.092 mv c squared, indicating a slight increase in mass shift with increasing invariant mass. Figure 1b shows the mass resolution, with a fitted function f x equals 13.9 mv jv times x to the power of 5 cubed mv c squared, revealing a significant decrease in mass resolution with increasing invariant mass. Figure 2a presents the mass shift of pi plus pi minus j psi as a function of the invariant mass, with a fitted function f x equals 0.96 mv jv times x cubed to the power of 5 squared mv c squared, demonstrating a moderate increase in mass shift with increasing invariant mass. Figure 2b displays the mass resolution, with a fitted function f x equals 2.07 mv jv times x to the power of 6 mv c squared, indicating a substantial decrease in mass resolution with increasing invariant mass. Figure 3 illustrates the confidence regions of the pole position in the complex energy plane, with sheet I and sheet 2 corresponding to different Riemann sheets. The gray region labeled "not allowed" indicates the region where the product gamma is negative, which is physically untenable. The confidence regions are shown for 1 sigma, 2 sigma, and 3 sigma, providing an estimate of the statistical uncertainty. The K-plane representation in Figure 3c offers an alternative visualization of the pole position confidence regions. These results provide valuable insights into the energy dependence of the mass shift and resolution of the d0 d0 pi 0 and pi plus pi minus j psi systems, which can inform future studies and phenomenological analyses. This paper presents a comprehensive analysis of the covariance matrices for pole locations on both the Riemann sheets and the K-plane, as well as their corresponding uncertainties. The covariance matrices provide insights into the relationship between different parameters in the system, revealing how changes in one parameter affect others. Table I illustrates the covariance matrix of the locations of the two poles on the two Riemann sheets, where Re, A, and Im, A, represent the real and imaginary parts of the first pole's energy, respectively, and Re, Eii, and Im, Eii, represent the real and imaginary parts of the second pole's energy. The values indicate a strong correlation between the real parts of the pole energies, with a weaker correlation between the imaginary parts. Table 2 shows the covariance matrix for the pole locations on the K-plane, where Re, K+, and Im, K+, are the real and imaginary parts of the first pole's momentum, and Re, K, and Im, K, are the real and imaginary parts of the second pole's momentum. Here, there is a strong correlation between the real parts of the pole momenta, and a weaker correlation between the imaginary parts. Tables 3 and IV present the upper and lower uncertainties on the pole locations on the Riemann sheets and the K-plane, respectively. These uncertainties are derived from various sources such as alpha, gamma d asterisk operator 0, efficiency, resolution, background, m, d0, ECMs, and simulation. The ranges of these uncertainties indicate the potential variation in the pole locations due to these different factors, providing a comprehensive understanding of the stability and reliability of the results. Overall, this study provides a detailed statistical analysis of the pole locations in a complex quantum field theory model, shedding light on the interplay between different parameters and their impact on the system's behavior.